Hey, it's Mr. P.
Good morning. Good afternoon, sir.
I've had a little bit of a problem there myself. Belle, how's it going for you?
It's going fine, sir. Just
Well, what's the
doing some
matter?
homework.
What's the matter?
Nothing. Just hmm?
What's the matter?
Nothing. Uh,
Come
Nothing,
on,
sir.
bitch to me.
Everything's going fine.
Come on, complain to me. I haven't had anybody complain to me recently. I miss it.
I'm just been I don't know. I've just been studying, taking my exams, just doing homework, the usual
Hmm.
work. So
So how much further do you have to
nothing much.
go, Belle?
Um, Pretty much. I think this year might be my last year. So
Okay.
before I decide to transfer
Where are you transferring to?
to I'm still unsure about that. As of right now, my number one choice would be UCF.
Okay.
But but
But you
I
got to go
might
to
decide to change
Orlando.
my mind.
Belle, you have to go to Orlando for that. I
Yeah,
avoid the Rat
yeah,
Kingdom at all costs. If I'm going to Daytona, I go via Miami.
mm.
I take it you like Mickey Mouse.
Kind of, kind of. I'm more of a Winnie the Pooh fan, though.
Ah,
Yeah.
well, good. It's a good school. So hey, and you know there are some aspects of Orlando. If you get downtown Orlando, it's kind of nice.
Yeah, I've been up there a couple times. So
Hey, I wish you luck. I wish you
yeah,
luck
thank
with
you
it.
so much, sir. Thank you.
Alex, you out there? Alex? Alex is shy today, Belle. Hold on, let me get my mic. uh, Hi, Kara. How you doing?
I'm all right.
Oh, good. Are you ready for a nice, quick night?
A nice quick night. Wait, well, oh yes, all day. All day. I'm sorry. I work all the time, so when I get here, I don't know what in the world is going on in my life. I'm just going. That's all I know.
There we go. There we go. Uh, yeah, I think this is my favorite St. Pete class. You guys are nice and relaxed, and nobody's freaking out too much, which is a good thing. How much longer do you have here, Kara?
I actually got to check. So I think this might be my last semester before they auto graduate me.
Ooh.
At least I'm hoping, because I'm actually loaded up on classes beyond what I should be doing, because I got to move for work as soon as COVID lifts the traveling
Uh-huh.
flag, because I'm a regional sales manager for work. So as soon as they lift the flag, I got to move out of the state of Florida. So I need to try and get my 2-year degree before I leave, because
Mm-hmm.
I'm at that cusp where if I
So
go,
where are they going to have you?
no.
Where are they going to send you? Do you have any idea?
So my region is from South Carolina to Delaware and everything in between. So I don't know where I can choose anywhere I want to move. Since mine's flood insurance, it's going to be around the coast.
Uh-huh.
But no matter what, you can't pay me to live in Washington, D.C.
Okay, I understand
No,
that. My
no.
advice is to avoid Myrtle Beach.
Really?
I hate Myrtle Beach. I really, it's just so touristy that it kind of makes my skin crawl.
See, I've only driven through it, so I don't know enough. I kind of have my sights set for somewhere in North Carolina, maybe like Wilmington or maybe like Hilton Head.
Hilton Head's in South Carolina.
Yeah, I'm okay with parts of South Carolina. I won't do Charleston because it's too crowded.
Charleston traffic is horrendous.
Yeah, it
It,
is. I've been
it's
there.
it really is horrendous. Hilton Head is real close to Savannah, though.
I'm okay with that. I like
Half
Savannah.
Actually, that's I was looking into Savannah hotels right before we got on the line here. So,
It's a nice
um,
area.
Madison, how you doing?
I'm good. I'm actually preparing for my flight in the morning.
Your flight? Where are you going?
To Seattle for the weekend.
God bless you. Have you
My
ever been
birthday-
there?
No, my birthday's next Tuesday, and me and my friend are going snowmobiling.
So you're going on Rainier?
Yes, sure.
Great, great. If you're in Seattle, there's a seafood place called Ivar's, Ivar, that is tremendous.
I love seafood, so we got to check that out.
Yes, absolutely. Ivars, and it's kind of a chain thing, but it's very, very good. There's also a great library in downtown Seattle. Not library, but bookstore. Fantastic bookstore.
Awesome.
And you have
I'm
to go to
super
Pike's
excited.
Market.
Is that the fish market?
Well, that's where they throw the fish, yes.
Yeah, people have been telling me I need to check that out.
Just be aware that Seattle it's very, very steep. It's very, very hilly there.
Yeah, I know the elevation is different,
Hmm.
but try not to get a headache.
No, it's not the headache. You're going to be walking up and down hills.
You're right. You're right.
Let's see.
I'm gonna switch to my computer real quickly.
Okay, no problem. Charlie, I see you made it in, Charlie.
Hi, I did. Thank you for letting me in.
No, I'm happy to do it, believe me. It's just a matter of just being prompted to do so. So I got 7 of, I got half the class in. Amazing. All right, guys, bar none. This is the most hated section in Chem 1. Every time I teach it, everybody tells me they hate thermodynamics. How far are you guys into thermodynamics? Have you gone through the whole thing by now?
I have.
Hess's law, the calorimetry aspects. Have you already had that, or are you doing it now?
We did that last week in my class.
Okay. How does it seem? Go ahead, talk.
Oh, in my class, we're kind of like, we just did Hess law last week, and we're doing a calorimetry.
Calorimetry.
Yes, this week.
Calorimetry is what we're doing tonight. Okay. And if you sit and pay attention, it's not that hard, but you got to be careful about signs, and you got to be careful about what temperature goes with what thing. Okay. So I got 9 people in here now. So I guess I'm going to go ahead and get started. This should not be that long. If I'm here more than a half an hour, I'll be surprised. All right. Calorimetry basically involves determining how much something can absorb heat or reflect heat. Okay, that's basically what calorimetry is. Kara, if you're trying, I'm trying to sit here and think what I want to do. All right, Kara, do you cook, Kara?
Yes.
Do you know the difference between an iron skillet and an aluminum skillet?
Yes.
All right. Now, Kara, if you take that aluminum skillet, you've sauteed something, you shove it in the oven, and you're kind of like braising it in there for about 30, 40 minutes, right? Are you going to reach in and grab that iron skillet?
No.
All right. On the other hand, if you take something like aluminum, if you ever put something under the broil with aluminum foil,
Absolutely.
and you kind of like take the aluminum out, and like 3 seconds later, you're able to crumple up the aluminum and throw it away, right?
Yes.
So would you say that the type of substance has to do with how much heat it can absorb?
Absolutely.
All right. Charlie? Charlie? I lost Charlie. Alex?
Sorry, I don't know why it wouldn't unmute. Hi.
No problem. Okay, Charlie. You're making pasta. All right. You're doing it for yourself, which means you probably use about what? Half a package of half a pound?
Sure.
Half a pound. So you don't need, you can use that, a quart. You can use a quart saucepan to heat up your pasta, right, Charlie?
Yeah, makes sense.
All right. Now, let's change the scenario. Instead of just making pasta for yourself, you have 8 people for dinner. So 1 pound of pasta is not going to make it. So you're
No.
going to probably use about 2, maybe 3, depending upon how big they're eating. Are you going to be able to use 1 quart of water to cook that pasta?
No.
So you're probably going to use something like a 5-gallon pot, right?
Yes.
So does it take longer to heat up that 5-gallon pot as opposed to that quart pot?
Yes, it does.
So would you say, Charlie, that the amount of stuff has something to do with how much heat it can absorb?
Yes.
Okay, Alex.
How much heat it can absorb, or the time it
Yes,
takes
or
to
the
absorb that
energy. The energy it's going to take to heat it to a certain temperature. It's going to take
Okay.
more energy to heat the 5-gallon than it's going to take to do the quart, correct?
Yeah. Okay, got it.
All right, Alex. Alex,
Yes.
do you like to take baths?
Not particularly.
But you have taken a bath, right?
I guess, yeah, when I was younger.
All right. Now, can you tell me, Alex, do you think it takes more energy to heat water to bath temperature, or do you think it takes more energy to heat it to boiling?
Probably boiling.
Boiling. Okay, so there are 3 things. There are 3 things that affect the amount of energy that you got to put into something to get it to a certain temperature. One is the type of substance it is. The second is how high you want to reach that temperature. And the third thing is the amount of substance. So there are 2 basic equations. All right. You guys may see the first equation as something that looks like MCAT, MC delta T. Is that how you were shown it?
Yes, I remember.
Yeah,
Okay. It's the same thing as MS delta T. I just use S because S stands for the specific heat. I like it better than C. No real difference. It is the same constant. Okay. So the energy I'm putting into a system is equal to the mass of that system times the specific heat, which is related to the type of substance I'm dealing with, times the difference in temperatures. Is this making sense, guys?
Yes.
All right. Now we have another equation we have to keep aware of. And that is the Q of my system is going to be equal to negative Q of my surroundings. So if my system gives up heat, that heat is going to be absorbed by the surroundings. System giving up heat is negative, exothermic. So it's going to be exothermic to the system, but the surroundings are going to gain that heat. So it's going to be endothermic for the surroundings. Is this kind of making sense to you? We have 2 equations we need to work with. Q is equal to MS delta T, or Q of the system is equal to negative Q of the surroundings. All right. Now, if I'm going to try and get the energy of a solid piece of metal, how easy is it going to be for me to do that? Because I got a solid piece of metal. How am I going to get the thermometer in there to try and get the temperature change of that metal? Is it going to be easy? Come on, somebody say no.
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 All right. So what we have to do is we have to do it by a roundabout way. Water is a very stable substance. So we know specifically that water has a very specific heat, 4.184 joules per gram Celsius, or 1 calorie per gram degree Celsius. It's very, very stable. We can measure the mass of the water. And we can measure easily, we can put the thermometer in before we do whatever we're going to do. Do whatever we're going to do, put the thermometer in afterwards. Where it's easy to measure the temperature before and the temperature after. Does that make sense to you guys?
Yes. it
So
does.
what we're doing is we're using water to figure out what the Q of our actual system is. And the actual system will be defined by the individual experiments. Is this all making sense, guys?
Yes.
All right. Let's deal with the first experiment. First experiment involves taking a piece of metal, generally speaking, a cylinder about that big. And what you're going to do is you're going to put that into boiling water and you're going to heat the snot out of it for 15 minutes. The reason you're heating it for 15 minutes is you want to make sure that the temperature of the metal is the same as the temperature of the water. Okay? But by the same token, you don't want to put any extra water on that metal. So what you're going to do is you're going to put that metal in a test tube and you're going to put the test tube in the boiling water. We have that right? Okay, guys?
Yep.
All right. So we're going to need to do some measurements before we start. First thing we're going to have to, we're going to need the mass of the water. So we're going to need to take the mass of our calorimeter. In this particular instance, it's 2.5609 grams. Then we're going to put our water into our calorimeter and we're going to reweigh it. And that's going to be 46.1603 grams. Okay, my test tube and metal is 91.5872. I take the metal out. I weigh just the test tube. That's 30.6600. Let me see something. Yeah, I put an extra 0 in here. So the weight of my test tube is 30.6605. Okay. What I did, I'm going to, while my metal is boiling away, I'm going to put the thermometer in the water. It measures out at 24 degrees Celsius. Okay. I take the temperature of the boiling water. The boiling water is 98.4 degrees Celsius. All right. Now, what happens when I put that hot metal into the room temperature water? What happens to the temperature of the metal when I take the metal, hot metal, put it in the room temperature water?
Isn't it like
Decreases?
The temperature of the metal is going to decrease. What happens to the temperature of the water?
Increases.
It increases. Okay. So we got to think what's happening in terms of exothermic and endothermic things here. The metal is decreasing in temperature. It's losing energy. It is exothermic. The water, on the other hand, is gaining energy. It's absorbing energy. Since the water is absorbing energy, it is endothermic. And what's going to happen is the metal is going to continue to lose temperature and the water is going to continue to gain temperature until they reach an equilibrium temperature. Is this making sense, guys?
Yes,
Talk
it
to
is.
me. Any confusion here? Charlie?
So they're just basically trying to get into the equilibrium to be equal.
Yes. What's
Okay.
going to happen? That metal is going to continue to lose heat, and that water is going to continue to gain heat until the temperature of the metal is equal to the temperature of the water. So what you have to understand is the final temperature, water and metal, is going to be the same. In this particular case, both of them are 29 degrees Celsius.
Okay.
So we got to figure out what's happening to my system. You can set it up where you get the mass of your water, the specific heat of your water, times the temperature difference of your water is equal to negative overall the mass of the metal times the specific heat of the metal times the change of temperature of the metal. You can set it up that way if you so desire. You'll get the same answer, but I think it's a little more confusing doing it that way. So I prefer doing it step by step, and that's how I'm going to show you how to do it. So if I'm going to figure out how much energy the water has gained, remember, that's an endothermic process. I'm going to need my mass of my water, the specific heat of my water, and the change in temperature of my water. My mass of water is going to be water in calorimeter minus calorimeter. I have 43.5994 grams of my water. My temperature difference. My water started off at 24 degrees Celsius. It ended up at 29.0 Celsius. So my delta T is going to be a positive 5 degrees centigrade. That's a bad number. My specific heat of water is going to be equal to 4.184 joules per gram centigrade. So in order to get the energy my water's gained, I multiply my mass times my specific heat times my change in temperature. My water has gained 912 joules. But remember, we said my metal is losing energy. My water is gaining it. So my water is a positive. My metal is a negative. That is why my Q of my water is equal to negative Q of my metal. So if this is true, then the Q of my metal is equal to a negative 912 joules. Here's where you got to be careful about your signs. What is my initial temperature of my metal? What did my temperature start out to be for my metal?
98.4.
98.4. So that is my initial temperature. Remember, delta T is T final minus T initial. Final temperature of the water was 29, so that's also the final temperature of my metal. So my delta T is equal to 29.0 minus 98.4, or I get a minus 69.4 degrees centigrade. Mass of my metal, stopper tube and metal, stopper tube, I subtract both of them. That ends up giving me 60.9267 grams of metal. Now all I got to do is plug these values in to Q is equal to MS delta T. My Q is negative 912. Mass of my metal is 60.9267. I'm solving for the specific heat of my metal. That's multiplied also by my delta T, which is a negative 69.4. So if I take negative 912 and divide it by 60.9267 and divide that again by 69.4, I get the specific heat of my metal. The specific heat of my metal is 0.216 joules per gram centigrade. Now, who believes in magic?
I do.
I do sometimes.
Thank you. Because what we have now is a magic formula. There is no rhyme or reason. There is no logic that I've been able to figure out to determine why this works. What happened is somebody just kept on plugging numbers in, and they found out that if you divide 25 by the specific heat, you end up with the molecular weight, the atomic weight of your substance. So if I have 25, I divide that by my specific heat. This gives me 116 grams per mole. Now all you have to do is look up on the periodic chart what the nearest thing to 116 is. And I think it's 10, if I'm not mistaken. Questions about part A? Anything you're not understanding about part A? Are we good then? All right. We have our part B. What we're going to do here is we're going to determine the heat per gram of dissolving salt in water. All right. Whenever you put a salt solution, whenever you put something into a solution, you will either rise the temperature or you will lower the temperature. The water is changing temperature. So your system actually is the ionic compound breaking up and dissolving in water. That is your system. Your surroundings are the water itself. Okay? So we are going to, again, we're going to put water into our calorimeter. And we are going to weigh our calorimeter so that we can get our mass of water. We're going to measure our initial temperature, which is 24.1 Celsius. What happened when I put my salt in there, it lowered. The temperature went down to 16.3. So my water lost temperature. And that was absorbed by the salt dissolving in the water. The mass of my beaker was 20.7543. The mass of the beaker in salt was 30.7603. This is all the information I need. All right? First thing I'm going to do is I'm going to find out what the Q of my water is. That's going to be the mass of my water, which is 52.9599 minus 2.5609, which is 50.3990. My delta T, my final temperature was lower than my initial temperature. So my delta T is a negative 7.8 degrees centigrade. So the Q of my water is my mass of water times the specific heat of water times my delta T. My Q on my water is equal to negative 1600 joules. But again, Q of system, negative Q of the surroundings. They're going to be opposite sides. So my Q of dissolution is going to be equal to negative the Q of the water. My Q of dissolution is going to be a positive 1600 joules. Now, that is 1600 joules. But how much salt does that account for? Our beaker was 20.7543. Beaker and salt was 30.7603. If I subtract these two numbers, that will give me the weight of the salt. So the 1600 grams or 1600 joules is due to dissolving 10.060 grams. If I want my delta H in terms of joules per gram, then I have to divide my total joules by the amount of salt it took to dissolve. So overall, in this particular instance, my delta H is going to be 160 joules per gram. Questions, guys?
Yes, I have a question. What is from the other slides? What is the cute water? Because I have the papers print out and it doesn't say cute water.
You have what printed out, Veronica?
The lab
What
in
does
the
it say?
so part A, it just tells you which one is the cute water, which is the heat absorbed by the water. But in part B, it doesn't tell you like which one is absorbed.
Okay, Veronica, I'm going to go through the lab once I get through this. Okay?
Okay.
Can you hold off a few seconds?
Yeah, that's fine.
Then I'll be able to look and see what you're talking about, okay?
Okay.
Remind me.
Yes.
Is everybody good about the calculations on this? We fairly good on that?
Yeah.
Yeah.
Okay, we're going to do a third experiment. The third experiment, we're going to take 50 milliliters of 2 molar HCl and we're going to mix it with 50 milliliters of 2 molar NaOH. Now, when I mix sodium hydroxide with HCl, they react in a 1-to-1 stoichiometry. Both of them have the same amount. Both of them have 0.100 moles. So they both limit each other. All right, keep that in mind. The limiting reagent I'm having here is 0.100 moles. All right, now you have to realize I'm putting 50 milliliters of essentially water with HCl, and I'm taking 50 milliliters of water with NaOH and putting them together. When I do that, I've got 100 milliliters of solution. So that when my solution changes temperature, it's because of that 100 milliliters. It's because I've added my milliliters of water and my milliliters of NaOH, and I have used the density of 1.02 grams per milliliter, which is the density of the salt solution. So to get the mass of the water in my calorimeter, I've got 50 milliliters of acid, 50 milliliters of base, 100 total milliliters. Then I'm going to multiply by 1.02 grams per milliliter, and this gives me 102 grams. Okay? In this instance, I don't know why this is. There's no earthly reason why this should be, but what happens is the temperature of your base and your temperature of your acid never equal the same. So in order for me to get the initial temperature, what I'm going to do is I'm going to average the temperature of the base and the temperature of the acid. In this particular case, my average initial temperature was 23.3. So I've measured the temperature of both the acid and base, then I've dumped the base into the acid, and the highest temperature that reaches is 37.4. So the Q of my surroundings, the Q of my water, is going to be the mass of my water, which is 102, times my specific heat, 4.184, times the change in temperature, which is 37.4, the final temperature, minus the average initial temperature. I do all that math out, and the Q of my water is 6,062 joules. Okay? But How many moles was that? Okay, I'm sorry, one more thing. This is the Q of my water. Remember I said Q of water, a Q of the surroundings is equal to negative Q of system. So if the Q of my water is this, the Q of my reaction is going to be negative 6062 joules or negative 6.062 kilojoules. This particular example, we need to determine kilojoules per mole. In order to determine the amount of moles, take the moles of your limiting reagent and multiply by the coefficient. Both sodium hydroxide and HCl are 0.1 moles. The coefficient is 1. So I've got 0.100 moles. So what I'm going to do is I'm going to then take my heat of my reaction, the negative 6.062 kilojoules. I'm going to divide it by 0.100 moles. This means that my reaction has an enthalpy of 61 kilojoules per mole. All right, write this down, ladies and gentlemen. Significant figures in calorimetry experiments are 95% of the time going to be determined by what delta T is. Generally speaking, my mass is going to have more significant figures than my delta T will. In this particular case, they're equal. If we notice the case before that, I've got 6 sig figs, 2 sig figs. So my final answer is going to be 2 sig figs. The first example, I have 6 sig figs, 2 sig figs. My final answer, that should have been 910 joules. So that's one thing I wanted to point out to you. Any questions about the calculations we're doing? Okay, now, Veronica,
Yes.
where are you talking about? I'm trying to figure out where you're at. Are you in the lab manual?
Yes, we're supposed to calculate everything, like to put the calculated data.
Okay, I've got the lab manual up. I'm trying to find out where we're at. Nope.
It will be page 83, if that helps.
Probably would if I was paying attention. Okay, we're in last week's experiment. Last week's experiment, and now we are in this week's experiment. Okay, now where are you talking about, Veronica? Page 83, you said?
Yes, when you go to like when it tells you the recorded data, the calculated data, I see that in the calculated data, in the part 8, go one more page down.
Oh. Ah. One more beyond this?
Right there. No, that one.
That one?
Yep. It says, you see in part A, it says heat absorbed by the water, which
That's
is
Q. If you
Yeah.
notice, all right, you see that's Q.
Yes, but what is it's Q on the second part?
I'm sorry, what is Q on the second part?
On the part B. So is it
Okay, heat absorbed by the water, it's the same thing as energy absorbed. Okay, you can't say absorbed because basically they give you different unknowns. Some of these salts are going to absorb heat, some are going to release heat. So where you see energy absorbed or released by the solution, that's where they're talking about that.
okay?
And this number, you see where my cursor is now, Veronica?
Hmm.
You see where my cursor is right now?
Yeah.
This number is going to be the negative of this number. These two are going to be the same in quantity, but the sign is going to be different. One's going to be positive, the other's going to be negative.
Okay.
If this one's positive, this one's going to be negative. If this one's negative, this one's going to be positive. Does that make sense, Veronica?
Yes.
All right. And for the last one, that's just going to be, Q is going to be right here. I'm sorry, Q of the solution is going to be here. This is going to be the opposite sign of this. Okay.
Okay.
Are we good now, Veronica? Do you understand what's going on?
Yeah. Thank you.
Anything else I need to do in the manual itself?
Mm-mm.
Okay, now I got to get rid of this thing. Okay, go back to table of contents. I'm going to take you through this is a pain to grade, which means it's a pain for you to do. This is probably one of the longer reports you're going to do this in terms of actual calculations. Preview. Everybody's seeing my slides, correct? You're
Yeah.
seeing this preview quiz
Yes.
and it's flipping over. You're seeing specific heat of a metal, right?
Yes.
All right. Question 2, worth 15 points. You got to give me the mass of the water in the calorimeter. You got to give me the mass of the metal. You got to show me what the delta T of the water is and what the delta T of the metal. Any questions on this? I'm
That's
here.
one that that's the one that is given, or the ones that we find out.
Okay, Veronica, you're going to have to go to the student data for labs.
Okay.
When you go to student data for labs, it will provide you with enough information to fill all of this information out.
Okay.
Okay? Question 3. Q of the water. You have the mass of the water, you have the delta T of the water. And you know that the specific heat is 4.184 joules per gram centigrade. Determine what the Q of the water is. Then determine the specific heat of the metal. You know from the Q of the water, once you figure out what the Q of the water is, the Q of the metal is going to be negative what the Q of the water is. You've got the mass of the metal. You've got the delta T of the metal. And you now have the Q of the metal. Solve for the specific heat. Any questions, guys? This one, if he only gives you one trial, just put in here one trial, or I think he only gives you one trial. I could be mistaken about that. But if he doesn't, do both trials and average them up. Unknown number, 3 points. Mass of the water used in the second experiment. Mass of the solid used. Again, show work. So all we're doing is getting the mass of the water that's in the calorimeter and the mass of the solid you're going to dissolve. Next question, delta T for the solution. Then you're going to have to get the Q of the solution. You're going to use the delta T, the mass, and 4.184 joules per gram centigrade. Q of the unknown, it's just going to be negative the Q of the solution. Delta H in joules per gram. You're going to take the Q of your unknown and divide it by the number of grams of salt you figured out in question 5. Heat and neutralization, change in temperature, Q of the solution. Remember, we got, use what they give you. He may give you 25 and 25 or 50 and 50, one of the two. Whatever the volume of the acid, you're going to add it to the volume of the base and multiply by 1.02. That will give you your mass of your solution. Multiply that by 4.184 and then multiply it by the change of temperature. That gives you the Q of the solution. Q of the reaction is going to be negative to that. Your enthalpy of neutralization is going to be your Q of reaction divided by the moles of your acid or the moles of your base. If you do multiple trials, average it out. That's it. Any questions on the report itself, the results?
No, looks good.
And unfortunately, I'm dead meat here. So I'm going to have to get out and come back in here, guys. Sorry. That was easier than I thought it would be. All right, calorimetry. Postlab calorimetry. Are you seeing preview quiz? Guys, okay, good. Gives you a problem. You got a metal weighing 121, has an initial temperature of 95.6, was put in 41 grams of water. The water was originally 21.7 degrees Celsius. At equilibrium, the water and metal temperature were 44.7. All this is it simulates the first experiment that you did. This. Okay. This instance. Okay. He's asking you, the metal starts at 95.7. Final temperature was 36.4. What is the change in temperature of the metal? Okay. Sets up another problem. You've got the weight of the water, initial and final temperature of the water, and you know what the specific heat is. How much heat flowed into the water? Okay. Same setup here. You've got the weight of the water, the change in temperature of the water. You can determine what the Q of the water is. That's going to be negative the Q of the metal. So you're going to then have the Q of the metal, you know the weight of the metal, and you know the change in temperature. Calculate the specific heat. So the 4 questions that you have here, they're basically nothing more than simulated questions based upon even the first part of the experiment. Anybody have any more questions, guys? Well, I got you out of here in less than an hour.
Thank you.
That says something anyway.
Thank you.
Thank you.
Anybody have any questions about anything?
We kind of learned about this already, at least in my class. So this is kind of a review.
And you're going to need it for the next test, Charlie.
Good.
All right. Nobody has anything, guys? I will see you next week then.
All right.
Thank you. See ya.
Bye.
Take care. Bye.
Bye.
Veronica, you doing okay with this?
Yes, I kind of took some notes while you were talking about it. And since you said it was long, I'm gonna start at least half of it today. And if I have any questions, I'll text you.
Yeah, if it's something you're not understanding 100%, it's better to do it earlier in the week. That way you can email me questions, okay?
Yeah.
Finest
Thank you.
kind. I will see you next week then.
Yes. Have a nice weekend.
You too.